Hi there, my name is Mark, and I look after product management here at Anjuna Security. We're a company that enables this technology that we'll talk about today, confidential computing, to be enabled very easily for organizations that are moving workloads to the cloud or perhaps exploring the frontiers of modern AI. So when we look at the technologies that have changed the world over the last 20 years or so, if we look back over technologies like the humble HTTPS, or TLS as we use it today, this enabled organizations to connect securely. And if you think about it, only 2 decades ago, organizations often used HTTPS on certain selective websites so that you could enter your password securely or enter a credit card securely. These days, it's absolutely everywhere, and it's been a foundational and revolutionary change that's let organizations connect with security end to end to move data around privately across the internet today. And in fact, we wouldn't work on the internet today without this technology, either inside or outside organizations. Similarly, firewalls, again, a technology that revolutionized the way that organizations could connect together. This fundamentally allowed businesses to interact online. It allowed organizations to isolate themselves to the extent possible back then with technologies that could block traffic going in and out of an organization. And again, it's something that you wouldn't go online without today, a foundational and highly useful technology. Confidential computing is one of those technologies in this realm of revolutionary change. In fact, I predict that over the next 5 or 6 years, we'll find that confidential computing is the default way that we compute. Why is that true? So it solves 2 fundamental problems that we've had with security technologies for many, many decades. Number one, it's to protect data in use. So that is code and data that can be used in any environment that ultimately is vulnerable in memory today, as we'll see. It's also about creating trust. And so with the pressure and focus on zero trust technologies and zero trust strategies, being able to prove and measure trust in the hardware before we start to use it is absolutely paramount for enabling the true vision of a zero trust strategy. So without these types of technology solutions, we have these 2 major problems. One is that data and code that's in memory today is largely unprotected. This is essentially code and data during use in memory or in processing. So if you think about it, you've got all manner of sensitive data in memory at any one time. We process credentials to authenticate users. We run code, including AI models, in active use. We might be encrypting or decrypting data coming from disk or from sessions over the network with that venerable TLS. We might have secrets in there that we want to protect and use for all sorts of purposes, whether it's Web3 processing or classic enterprise analytics. And so we have all sorts of highly prized data that's in use in memory. And when you think about attackers going after it, this is precisely the type of material that they're going for. And of course, trust is one of those things that is often implied. Perhaps we establish trust by looking at reviews of security operations. We might look at SOC 2 reports, independent assessments by third parties. But those are only a snapshot in time of when those assessments were done on infrastructure. And that has no real bearing on what the infrastructure is actually doing at the point that it's being consumed, which is right now. And you have to ask yourself, how do I answer the question of how do I really trust that the computation environment, like a cloud instance that you're about to use, can be entrusted with the most sensitive data that you're about to give it, be it the items on the left or highly prized sensitive personal customer details as we compute online. So confidential computing addresses these 2 problems absolutely head on. And it does this through a variety of mechanisms, depending on the nature of the processes involved. But ultimately, what it gives you is this notion of a walled garden around the entire application and data that you are putting up into the cloud. And so we're not just focused on protecting individual records here or individual pieces of data, or even just storage and in transit. We're thinking about protecting everything. And that includes the data as it's being consumed and used. Now, without this, cyber resilience itself is fundamentally limited. And of course, we can apply all the kinds of software solutions that we've attempted over the many years. We can embrace monitoring and so on, so we can see attacks happening in real time, but we're still not protecting the actual assets from compromise from the highest level of privilege. And this example is a great illustration of that. This was a great CISA report from earlier this year. It's on a red team exercise to attack critical infrastructure providers in the United States under a simulated basis. Well, actually, it was a red team attack on real systems. And what they were able to do was get in, dump memory, extract things like encryption keys, and then use those to decrypt other credential databases, allowing vast horizontal movement within the organizations, and in this case, for over 65 days without detection. And this is just one example of an organization that's got the capabilities to attack and extract things like memory, going after encryption keys. But if it's code or data or AI models, all sorts of damage can be done with that level of manipulation. Now, of course, the cost of a breach constantly goes up, but one of the things to think about here is that with memory largely being unprotected, a lot of these, the breaches that we see often start some way in memory, the manipulation of code, use of malware to scrape things from memory and so on, as in the attacks shown. And of course, there's this massive ripple effect that can impact organizations. So we've seen scenarios where organizations have had keys exposed, maybe from offshore attack groups. Recently, one of the hyperscalers went public about this, which was very commendable. And ultimately, it was a key that was in memory that was compromised, and then that the memory dump that was caused by an application that failed was moved to a production network, which was then attacked. And so you can see that these the kinds of attacks to memory can be far and wide, and especially when you're dealing with things like credentials, which might relate to credentials from third parties. If you're interested in more details of this, we've got plenty of blogs on the website going into these in specifically. So let's take a quick look at memory risks here. I'm going to actually show some of this in practice with just a quick demonstration. So what I've got here on the right-hand side is a classic AWS environment here. Let's see. So we've got an instance running in Amazon on the right-hand side. So this is essentially a virtual machine. It's in the cloud, fantastic security in the cloud. What I'm going to show you is this vulnerability to memory by illustrating through a very, very good product, which is a key management system. So what I'm going to do is run up a classic HashiCorp Vault system. So what you can see on the right, I've just booted that up. For those familiar, that's the kind of the startup screen. So I'm going to show that this is running. I'm going to issue a status command. I've done that on the right over here in the terminal. I'm going to now insert a secret into this environment, and I'm going to pull that secret back out. So pretty simple operations where we're running a Vault system, putting secrets in, pulling secrets out. But not because of the Vault software. The Vault software is exceptional in managing keys and secrets and so on. The fact that memory is vulnerable, even in this AWS environment here, means that if I have elevated privilege, like an attacker, like an offshore nation state or a determined insider or a curious SRE, I can go ahead and dump memory, which I've just done here. I've grabbed the process Vault and downloaded essentially the memory to a file. I can then parse that memory and very quickly get access to very sensitive data. And so, for example, here I've actually pulled the master secret straight out of memory. And again, once I have this credential, I could potentially cause havoc across other systems by decrypting other CRED databases, then using those credentials to move across APIs, lateral systems, and so on. So of course, the system I've shown here is a little contrived because I've been both the attacker and the admin, but I think you get the point. And we'll come back to this in a second. So when we start to look at this problem, of course, there are many reasons why organizations are somewhat hesitant to move applications up into the cloud today. This includes security as being one of them. When you're dealing with highly sensitive data, many organizations are hesitant because A, they don't feel they've had the level of trust and control for that workload going into the cloud. But it's also sometimes the lack of transparency on what's actually happening behind the curtain. And that lack of control conflicts with the fact that there's still a shared responsibility model with the cloud today. The liability stays with the data owners. And so confidential computing gives that control back. It allows organizations, even operating in the public cloud with workloads like AI, machine learning, or highly sensitive workloads, and move them to the cloud with total control. Now, confidential computing itself is generally broadly available technology infrastructure. Over the last several years, all of the major chipset vendors have added confidential computing to their core chipsets. So you have, classically Intel with its SGX environment, and now TDX that you've probably heard a lot about in the news. AMD has its AMD SEV processors. AWS has its own through AWS Nitro Enclave, and even NVIDIA now are launching confidential GPUs, which will give you private supercomputing power at your fingertips. Extremely exciting in the world of AI and generative AI in particular. But then, of course, all the clouds have very different ways that they've instrumented this. And yes, you can get off the ground with some basic confidential VMs, but to have the true isolation power of confidential computing and have it easily orchestrated and work within ecosystems that you'll use today, like Kubernetes, relies on having a software stack to be able to do that. And that's essentially where we come in as Anjuna as a mechanism to enable this to be simple and straightforward, irrespective of the cloud ecosystem. And so whether you're using this across different environments today, this is a single experience. So let's look at this from a use case perspective as well. So I'm going to get into the AI use cases a little more in a second, but typically there's kind of 4 or 5 areas that organizations are looking to solve, and confidential computing has a very powerful enabling capability in addressing them. Number one, it's moving those sensitive workloads to the cloud that are still blocked on risk and security and still stuck in the data center. So this might be core banking applications, payment applications that are very specific in nature, for instance, Web3 applications. And essentially, confidential computing can help provide the level of controls equivalence that you have in the data center for those operating now in the cloud. A really obvious use case is secrets protection. So one of the barriers for many organizations when they're embracing cloud is managing secrets. And yes, you can use hardware security modules, but they may not scale to the needs required, and in fact, may not have the functions necessary for cryptographic capabilities that you need today with agility. And so being able to use hardware isolated environments to protect secrets is another powerful and compelling use case, and we see that across the board, not just to protect the keys, but to run the entire cryptographic libraries and systems in this fully isolated ecosystem. But then the last two, which are really exciting and interesting and often come together, relates to data collaboration at scale and machine learning and AI on sensitive data. And so with organizations striving to achieve zero trust for these types of environments, hardware isolation of running code, data from multiple parties, for instance, 2 untrusted entities, fits very nicely into the confidential computing model and can be a springboard for things like secure AI at scale. So first of all, let's just take a quick look at an organization that's embraced this for the unblocking of the cloud migration challenge. And so I'm going to use a visualization to show this in a second and dive in a little bit here. So let me tell this story. If you haven't seen this before, it's pretty cool. So like many banks, this is an organization that had really started to close a lot of its branches around the world and still driving organizations to digital channels. And so it had scaled out its front-end ecosystem for the digital channels, so mobile banking applications, voice response systems, online banking, and so on, across many lines of business. But the back-end core transaction processing system and master databases were still running on that classic and venerable, but very powerful IBM mainframe platform. So in order to address the scale challenges here, the organization had created a caching tier. You see this thing called ODS here. If you look it up, it means online data store. It's a design pattern, if you will, to offload perhaps legacy environments, be it mainframe or Teradata and those sorts of things. So what this organization had done was scaled up its front-end systems, and then COVID hit. And unfortunately, more and more load was starting to appear on the digital channels, which was a good thing for digital growth, but on the back-end systems, they were struggling to keep up with the transaction volume. And with a very inelastic z/OS platform here, despite its power, that manifested as latency problems and very high cost on the back-end mainframe. So you ended up with users having issues on the front end of the apps. And transaction coherency issues and just general sluggishness. Not great for your customer sat scores. So what the bank wanted to do was to move this caching tier as an application straight up into the cloud. The challenge was that with the type of sensitive data we're dealing with here, millions of customer records, and also many, many keys, there was no desire for the bank to have keys and data present in the clear in the cloud, in memory. And so what it actually did was encrypted records up to the cloud, encrypting with AWS KMS, moving them up into a MongoDB caching tier, and then running the caching front-end systems in enclaves. So these green glowing cubes here, if you will, are these isolated points that can now use hardware to identify the application to the key management system, so reducing the dependency on credentials. And now as data flies back and forth to the front-end systems, it can be decrypted in this highly isolated walled garden, if you will, so that there's no personal data and no keys present in memory at any one time. And this allows things to be processed fully secure end-to-end in this hardware-isolated approach. Now, as it turns out, there are regulations that have emerged in the jurisdictions that this company operates in that are starting to demand data in use protection, particularly with the Bank of England. But certainly what we have here is a process that's been successfully migrated to the cloud without a lot of complexity and without refactoring, and yet having this massively increased bar with regards to security. When we think about AI, switching gears a little bit, I've talked briefly about the enablement of cloud migration with confidential computing, but AI introduces a whole gamut of new problems, particularly generative AI. Because you're very naturally, in many of these situations, creating a multi-party computation problem. You have model providers, that's one party. You have the operations infrastructure, the cloud, that's a second party. You have multiple data providers. Even inside a business, you might have one line of business that cannot share data with another, and yet there could be huge business benefits if that was enabled. And so you can have this multi-party environment that itself generates more risk and risk surface, and certainly introduces a gamut of privacy challenges too. At the same time, there's an absolute need to also protect and isolate models from IT internally. These may be third-party models, or it might be a model that the bank or the enterprise is building for itself and thinking about monetizing. If it's being trained on enterprise data, it could be extremely valuable. And so, as these stats show, many organizations have struggled with internal incidents and external attacks. And with generative AI, we introduce even more challenges too. So when we think about the classic ways we've been trying to protect data in things like generative AI, where you have new storage mechanisms like vector databases, you've got different kinds of inference models across the board, you've got the chat interfaces, the query interfaces, then also classical logging and monitoring and so on. All of this essentially has to be secured. And this requires a very different approach. It's no longer possible just to simply encrypt fields in a database or vectors in a database and have them decrypted into memory. The memory itself is highly attackable without a confidential computing approach. So here's an example So if you run an LLM like Surge, a simple or a relatively small chat enabled AI system, you can find all sorts of highly sensitive data when you dump memory. So you can get access to all kind of caches. You can see the end user's data, the chat history, and so on. You can also do things like potentially manipulate the models, the weights, and the parameters in the model itself. There's also the secrets, so how you connect to these environments and authentication tokens. And then if you really get deep into the weeds, there may be also billing data behind this as well. So there's a lot of attack points that, again, come back to the fact that memory itself is exposed. So again, if you think about having a hardware abstraction capability for protecting and running workloads, the same can apply to AI, whether it's generative AI or traditional AI. So the kinds of use cases that confidential computing solves here include protection of the models themselves. So let's say you're a business that needs to distribute a model to third parties. You might be an AI SaaS company, like the open AIs of the world and so on, where organizations don't feel comfortable about giving the data to a SaaS provider. Yet there's high value in being able to bring those models to customers. Well, certainly you have another problem. How do I protect that intellectual property as it goes into an untrusted environment in somebody else's compute? That's where confidential computing can actually solve that. It's kind of like a digital rights management for distribution of the models, including encrypting models so that they can run in trusted and measurable environments before sensitive data is applied. Then there's the other problem, the attack vector of manipulating the training data. And so being able to use some of the hardware attestation capabilities in confidential computing to guarantee that a model is training on trusted data from trusted systems that are operating in high integrity in confidential compute gives you that ability to shroud and manage that ecosystem so that trust can be established and proven during that training process. And yes, you've still got to make sure that the data is accurate and so on, but you can have certain assurances that it wasn't manipulated by the time it was used in the training. Then you've got the execution. There's the actual protection of the execution, similar to the first use case, being able to have protection across anywhere that that model scales across. And the last one, which is going to emerge as an even more important problem, is when you think about AI that is assisting not just us in chat systems, that's perhaps less mission critical, but certainly if it's making an actual decision, if you will, or an inference that's going to have an outcome that can drive a process. It might be a change in an industrial manufacturing process. It might be setting a price for goods. It might be deciding the structure of a HR organization to make systemic changes in the business. It's critically important in those circumstances to ensure that those outcomes were made on a system that has the utmost integrity from the moment that that code has run and from the build process that created it. And again, confidential computing addresses the protection during execution, but creates the trust environment to be able to prove and measure that, so that as those inferences are made, you know that there was integrity in the system, proof of processing. Very, very powerful capability that only a hardware-based approach can really truly resolve. So we see this at work today. I'm going to give you a couple of examples of this with AI in a number of scenarios. This one is a government agency. The problem at hand was automating the process of managing traffic violations by automatically scanning vehicles as they enter and exit roads, and then ensuring that the average speed was adhered to. And if you think about vehicles coming in and out of roads, might sound fairly benign, but there might be law enforcement vehicles, there may be government VIPs, there may be people and personal data involved, license plates, and so on. So there's sensitive data all round. So the challenge was that this organization had implemented this with an AI process running in a core data center. And as there were more and more cameras being added to the system, more and more data feeds, this system wasn't able to keep up with scale. And so we had a very inelastic system that was ultimately issuing traffic violations, and those were getting longer and longer and less friendly from a citizen experience perspective. And so by being able to move these types of infrastructures into public cloud, you're able to get this elasticity over the computation. You're able to manage the cost so that you're not having to have extreme levels of infrastructure in a data center for those peak loads. And we're able to also protect the models and isolate those from risk. So in this particular infrastructure, we had end-to-end encryption from the cameras all the way into the enclave environment, where the features were extracted, run into GPUs in this particular case, and then real-time notification for citizens. So you might not think that getting a speeding ticket almost instantly is a great experience, but at the end of the day, it's a better customer experience than essentially having something that's delayed or perhaps even inaccurate. Now, of course, with this, the organization is also able to think about how it can monetize the model. So being able to then offer this to other government agencies. And so you might see this at a country or a town near you soon, an AI-based traffic system, all enabled with confidential computing. Another quick example is in life sciences. And this is a common case when we're dealing with very large data sets and there's a need to enable clinical research or discovery across multiple parties. And so this was an organization that had looked to build this infrastructure themselves and realized that was going to be a difficult challenge. But at the end of the day, when you have a data provider, so for instance, it might be a healthcare organization, you have the model providers and maybe multiple model providers, and then organizations that might be drug research organizations or those developing new clinical processes and procedures, being able to benefit from this data, operating entirely privately, compliant to the myriad regulations that emerge, including ethical AI regulations, is a huge, powerful capability that can really raise the bar, not just for security and processing of data, but for the healthcare industry as a whole. And so confidential computing is a perfect fit for the kind of healthcare analytics that we've seen being made difficult by techniques like data de-identification and synthetic data that often damage data and reduce the effectiveness of models. Here we can use the live data across multiple parties with very powerful outcomes. So of course, to enable this, you need to think about this from what I'd see as a well-architected approach to confidential computing. At the end of the day, technologies that become ubiquitous, like TLS, like the firewalls, have to get there by being more or less frictionless. And so there are several design principles critical to enable a confidential computing approach. It ultimately has to be frictionless from the applications going into it. You don't want to engineer models to work in confidential compute. You want to use models, change them constantly, change the tooling, whether you're using TensorFlow today, PyTorch tomorrow, it shouldn't matter. This should be able to be used almost straight away out of the box. And it should also look at not just data in use, but being able to protect data from within that walled garden so it stays protected coming out, and so that you can control the engagement from one secure environment to the other, again, without having a lot of thought. But when you think about starting a workload too, there's been a long-standing industry problem of how you initiate secrets into the first time you boot an application. And with confidential computing, when ultimately you're looking to ensure that you have isolation of everything, the code and the data, the boot process and that secret injection should also be both secure and transparent. So it can become a more or less a set and forget scenario. And so there needs to be mechanisms so that you can fully embrace this technique, embody it into a CI/CD framework, and that has to be through this transparency as well. And last of all, when we think about making this ubiquitous and also very low impact, encryption technologies have always been both powerful, but also highly impactful. The nice thing with a confidential computing approach from a technology perspective is that the encryption that happens of memory and the isolation techniques also happen entirely in hardware. And so you have a very fractional overhead. We're talking a couple of percentage for the most part for workloads running in this environment. And that's very different to the traditional software-based approach to encryption that we all have known to always ask questions. How does this impact my performance? So this has to be minimally impactful and easily scalable. So let's go back to that scenario that we started with, and let's show how confidential computing can address this challenge here with exactly the same application. So first of all, let's kill that instance of HashiCorp Vault. I'm going to, first of all, just build a secure enclave here. So I'm taking what is essentially the HashiCorp Vault distribution out of the box as an application as is, and I'm going to build an image file and run this in AWS Nitro enclaves. So I'm not changing the application here. If you took something like Nitro enclaves out of the box, you'll get a very powerful isolated process or processing capability, but you won't have any of the subsystems that you need to run an application, like storage or networking or all of the classical things. So we're going to build the enclave image, add in those capabilities. And while we're doing that, let me show you a picture of what the Nitro system looks like here. So when we go to our AWS systems, we might procure an M5 large or an M7 large, maybe 16 vCPUs or 256 vCPUs. And we can choose to carve out, using the AWS Nitro enclaves, a number of processors that will be isolated from the rest of the system. And what this means is that these will be isolated by this vSoc layer back to the system on the left. So this is the host which connects to the rest of EC2 fabric. So we'll now quickly run a little network connection from the enclave to the outside world. And now we'll run HashiCorp Vault, very powerful key manager in the Nitro enclave itself. And the last piece here, there's two things. I'm just going to get the status of that enclave. And now I'm going to show that I can actually use it. I'm going to put a secret in, same procedure as I did before, take a secret out. Now I'm going to attempt to dump memory. I'm trying to even find the process. It doesn't exist as far as I'm concerned. So now I've isolated completely this application that was essentially vulnerable because of memory attacks, and it's no longer attackable, even though I have root level privilege. I cannot observe it, cannot dump it, and so on. But the application still works just as it did. So that's kind of going from vulnerable to protected in just seconds. So if you'd like to dive deeper on this, you can see here we've got a Gartner report you can download that's a really good survey on AI. And on the right, more details of our technical capabilities and technical deep dive on how confidential computing can solve AI challenges. Do get connected here as well. You can connect with me on LinkedIn. Couple of really important things. We have a CSA working group on confidential computing. It's looking at how this applies to the cloud controls matrix. The link's here, but just ping me. You can get in touch and we'll get you involved. And last of all, if you'd like to dive deeper yourselves, we have confidential computing workshops and software technology that you can try this out yourself as well. So thank you for watching. Much appreciated and looking forward to connecting. Thanks so much.